Segment 4 for Chapter 9, we're going to get into molecular orbital theory. So we've introduced it a smidge, but now we're going to get into some details about it. So molecular orbitals are going to be associated with the entire molecule as opposed to one atom. So we looked at atomic orbitals, and now we're going to look at molecular orbitals. It's going to allow us to accurately predict magnetic properties of molecules. So by looking at the electrons and seeing how they are situated within the molecule will tell us whether or not we should expect it to be magnetic or not. Energies of molecular orbitals determined by combining electron waves of atomic orbitals, right? So it could be the energies of molecular orbitals determined by combining electron waves of the atomic orbitals. So they're going to come from various combinations of atomic orbital wave functions. So for instance, we're looking at H2, we have two 1s wave functions, one from each atom. They'll combine to make two molecular orbital wave functions. So in other words, if I have one S from an A hydrogen plus one SB second hydrogen, when we combine them, we're going to have a bonding molecular orbital. So combined means we're going to have an overlap, and then the bonding MO itself will be that look where it's all cohesive in one piece. So it's going to be, there's constructive interference of the waves, right? The energy of the bonding MO will be lower than either of the atomic orbitals. So remember, electrons move based upon energies, and so if I want to form a bond, then it has to be advantageous to the electron to form that bond, which means there has to be a decrease in the energy. There's got to be a reason why the electron wants to go there rather than stay where it is located presently within the atomic orbital. Now, that also means that when we generate a bonding orbital, we're going to generate what's called the antibonding or the sigma star molecular orbital. So the number of atomic orbitals must equal the number of molecular orbitals. So if I have two hydrogen atoms, each bringing a 1s orbital, then there has to be two orbitals in the MO, and that means we're going to have one that's going to be a bonding orbital and one that's going to be an anti-bonding orbital. So here we could have the constructive additions of those waves or the deconstruction of those waves. So another possible combination of the two 1s orbitals would be 1sa minus the 1sb, and now we get an anti-bonding MO, so the destructive interference of the 1s waves. The energy of the bonding molecular orbital then is much higher than the energy of the parent atomic orbitals, and of course we know the electrons then will not want to go into that orbital. So the summary from an MO then, for 1s atomic orbitals, if I take the two hydrogens, we're going to overlap them, and we're either going to get a bonding orbital or we're going to get the anti-bonding orbital. So actually, if we combine them this way, we're going to get both. Don't mean this to make it sound like it's either or. When we combine these and we look at it as an MO, we get both the bonding and then non-bonding. Now, bonding molecular orbital electron density builds up between the nuclei. Electrons in bonding MOs tend to stabilize the molecule. The anti-bonding will have the cancellation of those electron waves, which reduces the electron density between the nuclei. And of course, electrons in the anti-bonding MOs tend to destabilize the molecule. Now, we're going to draw an energy diagram here, and the energy diagram is going to look sort of similar to what we had before, sometimes a little different. So I'm going to go ahead and put this up, give you a moment here to kind of take it in mentally, kind of work through it and digest it a bit, and we'll explain what's going on. So if I kind of think of the picture as where I have these dotted lines, sort of like that, these are our atomic orbitals on the outside. And then our MO is actually here in the middle. Okay, so this is going to be the molecular orbital. These are going to be the two atomic orbitals. So whatever atoms I'm looking at, I'm going to put on the left and the right, and then how they stack up together will be the molecular orbital. All right. So here we have the hydrogen with 1s electron, hydrogen 2 also with a 1s electron. In the middle, remember, we're going to make a sigma bonding orbital that's going to be lower in energy than both of the parent orbitals, but we're also going to make a sigma star, our antibonding orbital, which is above energy, so higher energy than either one of our atomic orbitals. So H2 is a very stable molecule because what I'm going to do is start to take these electrons and put them in the middle. We get 1s going to the sigma 1s. We get 1s going to the second sigma 1s. That means we have 2 electrons in our bonding orbital. We have 0 electrons in the anti-bonding orbital. So this should be a very stable molecule, and of course we know that it is. So rules for filling your MO energy diagrams. Electrons always fill the lowest energy orbitals that are available, right? It's basically the Aufbau principle. It was the same for atomic orbitals. It'd be the same here for molecular orbitals. No more than 2 electrons with spin paired can occupy any orbital. That sounds familiar as well, right? That's the Pauli exclusion principle. Electrons spread out as much as possible with spins unpaired over orbitals of same energy. And again, that's Hund's rule. So we're applying a lot of the same rules for atomic orbitals to our MO and seeing how that works out. Now, a new topic that will come out of our MO is going to be the bond order. So bond order is a measure of the number of electron pairs shared between 2 atoms. And the way we'll calculate that is we'll take the number of bonding electrons minus the number of anti-bonding electrons, and then we'll divide that by 2 electrons per bond. That'll give us a bond order. So if we go back and look at H2, we had 2 electrons in the bonding electrons. We had 0 in the anti-bonding. So 2 minus 0 divided by 2 gives us a bond order of 1. And a bond order of 1 will correspond to a single bond. Bond order of 2, double bond. Bond order of 3, triple bond, right? All right, so the MO energy diagram for helium-2, right? So we're going to see why helium will not form a bond with another helium. We now have 4 electrons, so both the sigma and the sigma star molecular orbitals are going to be filled up. That means our bond order would be 2 minus 2 divided by 2, which is going to be 0. Okay? There is no net bonding, so therefore He2 does not form, and of course we can't find that as a molecule in our everyday world. All right, so what happens when we start to introduce the 2p, right? So if we want to get a little bit bigger here and get beyond hydrogen and helium, then when we add the p orbitals, we're going to see sort of the same thing. So here we could have the PZ, 2PZ, 2PZ, they could go plus minus, they could go plus minus. Here they could go plus plus, which would give us an overlap. It's the same idea. Energy here is going up. So here we would have a bonding P. Here we'd have anti-bonding P. So sigma versus sigma star. Now remember, the other thing we can do with our p orbitals is we can make pi combinations. And so we'll see the same thing here. We can get a pi or a pi star. Now the difference will be, because we have 2 p's, we can actually do more than just 1 p at the same energy level. So when we go to draw out the diagram, it's going to look a little bit more like this. So when we get to those p orbitals, we can start to overlap with the pi here. So we have our s star, sigma, sigma star. Then you can see we're going to have 2 py, pz, and px stacked just like that. Or we could stack them this way, where we have 1, then 2, then 2, then 1. All right, so a couple of different ways here. So if we look at Li2 going to N2, the pi 2p is lower in energy than the sigma 2p. All right, so we see that here our sigma is actually higher in energy than our pi. And then O2, F2, and higher, that we have a lower energy in the 2 pi. So now the 2 sigma is lower in energy than the 2 pi. All right, so lithium through nitrogen, we see that the pi is actually lower in energy than the sigma, but for oxygen on up, we see that it's going to be the opposite. Now, diatomic molecules in the second row elements, the 1s orbital is smaller than the 2s. So for lithium, the overlap of n would equal 2 orbitals, will be much more than the 1s. Also for 1s orbitals, they'll both be completely filled. So both the sigma and the sigma star molecular orbitals formed from these are going to be filled as well. Therefore, there's no net bonding. Now that means we can also ignore the 1s. Since we filled the 1s, we know that it's going to be a 0 as far as that works out every time, which means we can focus on just the valence electrons and the outer orbitals. So for our MO energy level for Li2, again, we won't worry about the 1s. We know that that's going to make helium and cancel out. So we're going to look at the 2s and the 2p. So for lithium, let's see, we know the electron configuration would be helium 2s1. So we'll put 1 electron for lithium 1, 1 electron for lithium 2. They both go together and make Li2. So the bond order here should be 1. So the Li-Li single bond, in theory, should be a stable molecule. Now, it is diamagnetic as there are no unpaired spins. So that's how we can tell if we're going to have magnetism or not. If we have a lone electron in any of our orbitals, then we'll have an unpaired spin, and we would expect that to be paramagnetic. So if we look at Be2, we know now we're looking at the 2s2, so we'll have 2 electrons in our 2s's. When they fill in, we'll fill in the sigma 2s, but we also fill in the sigma star 2s. We come back to a bond order of 0, and so we would not expect this to form, and of course we find it does not. All right, so moving right along to boron. So now for boron, we have the 2s2, 2p1. So now we know we're going to have 1 electron from each boron in the 2p. We know that the 2s's are going to cancel each other out. We're then going to put 2 electrons. Now remember, because we're still not quite to oxygen yet, we know that the pi is going to be lower in energy than the sigma for this. So we're going to fill in those 2 unpaired. So now we get 4 minus 2 divided by 2 gives us 1. So the boron-boron should be a single bond and form a stable molecule. Now, the other thing we'll notice is that it's got 2 electrons that are unpaired. That makes this paramagnetic as it has 2 unpaired spins. And this is how we know that the pi is lower in energy than the sigma. You see, if the sigma was lower in energy, then boron would be dimagnetic because they'd be paired up. But since they're not paired up, we find that it is paramagnetic, and therefore the 2 electrons aren't paired. All right, so we're moving right along to carbon then. Again, the 2s is going to be pretty boring down there. We'll start messing with the 2p again. First, we're going to fill in the 2px and the 2py, and then we're going to pair them up. At this point, we now have 6 minus 2, or a bond order of 2. So we'd expect the carbon-carbon to be a double bond as a stable molecule. Again, no unpaired spins. It continues to be diamagnetic. For nitrogen, now we have 3 electrons in the 2p for each atom. The 2s again will cancel out. We'll fill in the 2px and the 2py, and then we'll fill in the 2pz. That means we have 8 minus 2 divided by 2, which should give us a bond order of 3, meaning the nitrogen-nitrogen triple bond should be a stable molecule, and once again, diamagnetic. There are no unpaired spins. We get to O2, and now we're going to see that it flips. Remember, the px-py is now higher in energy than the sigma. We're going to fill all the way in, and then we're going to get 2 unpaired electrons in the star. So now we're going to get 8 minus 4, which means we should expect a double bond for the oxygen. However, it's paramagnetic because it has 2 unpaired spins. Now, what's interesting is the Lewis structure couldn't tell us that. Okay, so again, we can use different orbital theories, different bonding theories to explain different experimental observations. Okay, that doesn't mean one is right or one is wrong. It just means that each one is giving us a little bit more of the story so that we can see the entire thing. For F2, we now have 7 electrons in each atom. Our sigma star and our sigma for our 2s will both be filled. And then we'll begin to fill our 2p. And of course, now we get 8 minus 6 divided by 2 gives us a bond order of 1. And the fluorine-fluorine single bond, of course, we know is a stable molecule, and again is diamagnetic. Finally, we get to neon. And of course, we fill everything in. And we see now we have 8 minus 8 or a 0 bond order. And so neon-neon does not form and is not a stable molecule. All right, so that was all of our diatomic molecules. What about our heteronuclear diatomic molecules? So if lithium through nitrogen pi 2p is below the sigma 2p, and if oxygen and fluorine in higher atomic number than sigma 2p below the pi 2p. So example, BC both are to left of nitrogen, right? So if I look at boron carbon, so the 2 pi is below the 2 sigma again. OF though, both are to the right, so now the sigma is below the pi. But what about NF, right? So we have fluorine. Fluorine should be below, but in the nitrogen we should see it above, each one away from oxygen, so average is oxygen, and sigma 2p below pi 2p. So what is the bond order of NF and BC? So for BC, the number of valence electrons would be 3 plus 4, which is 7. We know that the the pi 2p would be lower, so we're going to have the 2pz here, the 2px and 2py together on the same energy level. We would fill it in, and we see a bond order of 1.5. Now that might feel a little weird to see you have 1.5 bonds. This is normal. Don't freak out when you see a half. It's okay. For the NF, where the sigma is lower, now we get 5 plus 7 equals 12. We put our 12 in, and we end up with a bond order of 2, 8 minus 4. All right, so now that pivotal one, what happens when we have nitrogen, which we expect to be this way, oxygen and fluorine we expect to be this way. We put it together with NO, it gets tricky because the nitrogen predicts that 2p would be, the pi 2p would be lower. Oxygen predicts that the sigma 2p would be lower, but we have to look at the experiment. So that's going to show us that the sigma 2p is actually lower. So we're going to write it this way. The number of valence electrons here will be 11. So we'll fill that in with only one electron going up to the 2px star. The bond order here should be 2.5 this way. Okay. All right, so what is the bond order then of NO plus and NO minus? So we can do the same diagram, right? We already know that from experiments we expect the 2pz, the sigma, to be lower in energy than the pi. So we can write it that way. We do have a different number of electrons though, right? For the NO plus we have 10 valence electrons, right? That means the bond order then is going to go 8 minus 2 divided by 2 is going to give us 3. For the NO minus, we're going to add an electron, so we're going to have 12 electrons, and now we're going to have 8 minus 4 equals, divided by 2 equals 2. So for NO plus, we actually get a bond order of 3. For NO minus, we get a bond order of 2. Now, how do I compare the relative stability of NO, NO plus, and NO minus? Now recall that bond order increases, bond length decreases, and bond energy increases. So if I'm looking at NO plus, we said we had a bond order of 3. The length is 106 picometers, and we get a nice high bond energy of 1025. For NO, we got a bond order of 2.5. We see that length kind of extend out, and of course the strength weakens down a little bit. And for NO minus, we get a bond order of 2, and we see that we have 130 as our length, and then 400 is our energy. Right? So we see the bond getting longer, and we see the bond getting less stable. So NO plus is the most stable form. It's got the highest bond order and the shortest and strongest bond. All right, your turn to play with these things. The bond order and whether or not a molecule is parameric or diametic can be determined by looking at the formula, the Lewis structure, only by drawing the MO diagram and filling in the appropriate number of electrons, by intuition, or from valence bond theory. And of course, that's what we just did, MO diagrams, right? So that's got to be the answer. All right, which of the following species is paramagnetic? So you might have to take some time here, hit pause, draw these out. put your molecules in, excuse me, put your atoms in, draw your electrons in, and see what the MOs look like. Hopefully you come up with D, N2 with a 2 plus. What is the bond order for each species, and how many unpaired electrons are there in O2, O2 plus, and O2 minus? Again, you might have to push pause, draw these out, and see how it goes. And hopefully you come up with E, 2, 2.5, 1.5, 2, 1, and 1. And of course, if you flip back, we did O2 together. So you know O2 had a bond order of 2, right? And we know we had 2 unpaired electrons. If you move to the O2 minus, you're going to add an electron there, which means you're going to make a pair of electrons. So that's how we get down to 1. But you're also taking away from that bond. So that's how we get the 1.5. For the O2 plus, we're taking an electron away. So now instead of having 2 unpaired, we only have the 1 unpaired. But that is going to increase our bond order. So it's going to go up by an electron, which means it's going to increase by half. All right. We're at the 21-minute mark, so I think we're going to stop this segment here, and then we're going to compare the two, valence bond theory versus molecular orbital theory, and see how that works out for us, right? So when to use which one, or do we use them all? And I think I already kind of gave you that. So, you're going to use whichever instrument is going to give you the data that matches the experimental observations. All right, so stay tuned. Be back here in a few minutes with our probably 5th and final segment.